Hi everybody. Today we will get into current resistance and electromotive force. Actually, this electromotive force or voltage. It's not the force, but it's the voltage or the potential difference we will see. The current is defined as dq over dt, just like the velocity defined as dx over dt. This is the charge per unit time. So the current is passing through this wire. Okay. Remember earlier we had charges, but now the charges are moving. So charges are moving with some kind of velocities, and we call this velocities as drift velocity. Okay. We assume that the positive charges move in the same direction with the current, but actually it's not the case. The real scenario is that electrons move in opposite direction, because electrons are the ones which create the currents, not the positive ions, copper or aluminum or any other metal you are using. If you look deep into this wire, okay, you will see that when we have the current this way, okay, the current going from left to right, the electrons are moving this way, exactly in opposite direction, but not straight. Okay, the electrons will make lots of collisions, and electrons, okay, collide with atoms and other electrons, and they do some kind of this kind of zigzag motion. Okay, so they just collide with and they change the direction, but on the average they drift to the left. Okay, to the left. So the electron starts from this point, and then after some time it ends with this point A, point B, but between A and B some kind of time is passing. So suppose that this is delta t, right? Delta t is the time between A and B. In this case, if we measure the distance like delta x, here, delta x, the velocity, which is called the drift velocity, will be given as delta x over delta t. Okay? Delta x over delta t. So, as you see, electron is making lots of collisions until coming from point A to B because of this drifting, but the current is flowing from left to right. So we can treat this as if positive charges are moving along the current. But now there is also another thing which is very important. In order the current to move from one point to another point, let's say this is point A here, right? This is point A and this is point B, just like the cable here. Okay, so in order the current to move from one point to another point, the left part, the potential on the left should be greater than the potential on the right. So if we say that this is VB and this is VA, VB must be greater than VA in order the current to flow from left to right. If VA is greater than VB, then the current will flow in opposite direction. So we learned something now. Remember earlier we had hanging charges, but now the charges are moving. The current is this way. So if this is VB and this is VA, here VB should be greater than VA. For instance, this may be 5 volts, this may be 2 volts. But now if the opposite is true, okay, this is VA, the current now will flow in the reverse direction. In this case, VA is greater than VB. Okay, VA is greater than VB. So the current, which is defined as the charge per unit time, now can be explained by the potential differences. Now also, if we look at here, if you look inside the cable, okay, the net electric field is always in the direction with the current. Since VB is high potential than VA, there is a net electric field this way, okay, inside the cable. But later we will see that these kind of collisions for electrons are only when there is current, the electrons can move freely when there is no potential difference is applied. But as soon as the potential difference is applied, all the electrons move to the surface, and they move to the surface, although they do also similar kind of collisions on the surface, same thing, okay? But so drift velocity will be given by this expression. Drift velocity is not really very fast, although the current, as soon as you turn on the switch, suppose there is a switch here, okay? As soon as you turn on the switch, the current seems to start instantaneously, but the drift velocity is not very high. So if electric field is in this direction, the electrons will feel the force in this direction on the average, of course, right? Because F equals, let's write this expression also, F equals QE, and Q is minus E electric field. So the force and the electric field directions should be opposite to each other, just like I have drawn here. So we are really not interested in what kind of electric field we have, what kind of force we have, because what is important for us now is the current and potential differences, okay? The electric field, we know that, of course, there is an electric field, but we are not really so much interested in that for the time being. So as you see, when the electrons are moving with drift velocity, it looks like the positive charges are also moving with some kind of drift velocity. So this is how we just visualize the current, okay? But now look, let's look at the problem closely. This is the cross section of the cable, and if we look at this cylindrical surface, okay, this circular surface, okay, and suppose the positive charges are moving with drift velocities, okay? Of course, electrons are moving in the opposite direction, but the same thing, okay? We're just considering this for the time being. And we know electric field is in this direction, so that the positive charges are moving in the same direction with the electric field. And also, we have potential difference. This is B, VB, and VA. And VB being greater than VA. In this case, the current is in this direction, okay? From left to right. So the positive charges looks like moving from left to right, passing through this cross section. Okay, so the area of this is A, but now the thing is that we have now the current is also given as, this is the current. The current is given as dq over dt. Okay, let's write all these expressions on the side. Now, what we would like to show that we would like to find the volume of the cylinder, the volume of the cylinder. Volume of this little cylinder is just delta x here, okay, times the area, okay, because this is how you get the volume. If you have the base area and times the height, you get the volume. So it's delta x times area, okay. The volume is given. But now, what about the number of particles? The number of particles, positive charges, let's say, not particles, but let's say positive charges, number of positive charges in this volume, okay, is given as, okay, first let's define the concentration, okay. The concentration is given as the number of particles divided by the volume. So the number of particles is given as concentration times the volume, okay. So in order to, sometimes this concentration is shown by a small letter n, okay. So the number of particles is just n times the volume, but the volume is delta x times a, okay. Now, since we know that delta x can be written as Vd times delta t, because one particle enters this positive charges enter to the left side of this little slab and then leaves the right side, and delta t is passing, so the drift velocity is given by delta x over delta t. In this case, delta x can be written as Vd times delta t. Okay, so n Vd delta t, the area is there already. Okay, so we have now this is the number of positive charges within this volume, not outside, just within this volume. But now, look, what about the total charge in this volume? Total charge in this volume is given as n times q, because each charge is q, right? Each charge is the same, because we have the same material, the same kind of charges moving. Actually, electrons are the charges. So q is E. And don't forget, q is always E, because the charges are electrons. And also these are positive E, and the electron charge is the negative E. Okay, so now we have, what we have is that dq will be, okay, dq will be equal to, okay, dq will be equal to q times number, dn. So the thing is that now when we have, as soon as we have delta x or delta t on the right hand side, we have to write this as dn, okay? Because this is just a little bit time, this is just a little bit distance, and the left hand side is just a little bit charges inside this volume. So this expression is correct, okay? So that's why we have now multiply the charge by dn to get dq. So from this, we see that if we multiply this expression by charge, we get dq, because we are coming to current, you know, dq. So n vd q times delta t a. So instead of delta t, it's better to write dt, because we have dq there. Or if we write delta t, we have to write delta n there. So delta t, delta x, delta n, or dn dq. Okay. So if you look at the left hand side, it's dq, just a little bit charge and just a little bit time. So if we divide this by that, dq over dt, which is just the current, remember that this is the definition of the current. So we'll be given as nvd, okay, times q area. Okay, so the current is given by this microscopically. So now we see that the current depends on many things. First, how much is the drift velocity? What kind of charge is moving? But this is just E, we know it's electronic charge. What is the cross section of the wire? It's very important. And the number density, okay, the number density or the concentration. Number density is concentration or the number divided by the volume, don't forget. So little n, which is the density, is just n over volume. Always keep this in mind. So, of course, this n depends on what kind of material you are using, and the drift velocity also depends on the material you're using. For copper and aluminum or some other iron, some other metals, these drift velocities will change. Okay, so this is my microscopic point of view, right? Of course, we will solve some problems with this, but there is another definition I would like to make at this stage. This is the current density. Okay, current density. For current density, we use J, and it is given as the current per unit area. Current density is called the current per unit area. And if you look at this expression, if we divide the current by the area, which is on the right-hand side, it's just NVD times Q. As you see, this is all related to the material, okay? What kind of material you're choosing gives you this. And number N, okay, number N, the number of particles within this volume also depends on how much potential difference you're applying to the wire, okay? So, or how much electric field is there and how much force is on the positive charges, okay? So for the positive charges, the force and the electric field direction is the same as you will remember, okay? So now, if the force is greater, then obviously what we will have is that we will have more force on the charge, so that at an instant we can see more particles for okay, bigger amount of potential difference. Okay, so the definition of the current density is this. As you see, the current density is related to the velocity, and velocity is a vectorial quantity, so that we can say that J is just NQVD. So, okay, it's the current divided by area, but it has a direction with the drift velocity. And don't forget that drift velocity is not straight velocity. It's just the velocity that the electrons move with, but due to the collisions, this velocity is not really great. Actually, electrons are so free to move within the conductor, but when there is no electric field or the potential difference is applied, the random motion is such that electron starts the motion at point A, makes lots of collisions and come back really near A. So there is no net drift, okay? But when you apply an electric field, then the electrons will drift to the left slowly. So this drift velocity is not really great. Okay, so now we learned how we continue. We learned how the current is created in the wire. Now we go on and really understand how much this material creates some kind of resistance to these electrons and the charges. So it's very important. Unless we know the resistance, which is the first basic circuit element that we will use, okay? Actually second, because the first one was a capacitor, don't forget. The second one that we are now doing is now the resistance. Later on, we will combine the capacitance and resistance and do some experiments of charging the capacitor or discharging the capacitor. And okay, we will see that the time for this charge and discharge depends not only on the capacitor but also on the resistor. Okay, so now let's get into the resistivity business. So how can we define the resistivity? Each material has some kind of resistivity, and this resistivity is given as, it's not the density but resistivity. So maybe it's better to put a subscript R there, because rho was the density, remember? So the resistivity is given as E over J. So the electric field divided by the current density, okay? This is how the resistivity is defined. For instance, for silver, rho R is like 1.5 times 10 to the minus 8, very small. And the unit of this is ohm meter, okay? We will see that resistivity or resistance is ohms, and ohm meter is the resistivity. So for silver, it's very small, as you see. For copper, resistivity is 1.7 times 10 to the minus 8. So silver is much better conductor, but of course more expensive. Gold, which is the most expensive one, has a much better 2.4 times 10 to the minus 8. As you see, they are similar, but there is a slight differences, okay? So gold has, gold has the resistivity which is greater than the others, okay? And I will show you why this is happening. Okay, but mercury, for instance, the resistivity is 22 times 10 to the minus 8. So gold is more resistant from copper, and it is more resistant from silver. So So this all depends on the material, by the way. But when you see pure silicon, for instance, the resistivity is 2300. How many orders of magnitude greater resistivity the silicon has comparing with the others? As you see, it's like about 12 or 13 order of magnitude. Okay, right? So silicon has extremely big resistivity. And glass, for instance, glass, because these are called non-conductors. Non-conductors have much higher resistivities. Glass has about 10 to the 10 to 10 to the 14 ohms meter resistivity. Very high. Teflon, for instance, this is something that we use in technology, is greater than 10 to the 3, 10 to the 13. Okay? So basically, these are non-conductors, but these are conductors. As you see, very small resistivities we have for the conductors, but for the non-conductors, we have great resistivity. Of course, because the current cannot easily flow through the non-conductors. We know it already. Okay, so this is basic introduction. But, you know, resistivity will change in time, will change by the temperature. So here is the resistance, right, we have. I'm just putting a few resistances here. Okay, this is a very small resistance I have now. And when we are giving this lecture, I would like to show you these things. Also, I will make a little experiment along the way. Okay. So as you see, these are the resistances that we use in our circuits, right? Very small ones. Okay, and also this is quarter watt, this is 1 watt, and this is the 5 watts resistor. And when the current is passing through, these resistances will get hotter. Okay, when they get hotter, okay, when they get hot, their resistivity changes. It means that their resistance changes. So if it is 5 ohms, when the current moves through it, it increases a little bit, because the temperature increases. Also, if you do the experiment here in the room temperature, suppose the resistance is 5 ohms, but if you do it at a really high temperature, very hot weather, in this case, the resistance will increase slightly. And the expression we have for the resistivity is, at any temperature, is given by rho 0, okay, plus rho 0 alpha times delta T, T minus T0. T0 is room temperature. We assume that room temperature is about 25 degrees, okay? And rho 0 is the resistivity at room temperature. Resistivity at room temperature. As you see, when we have the temperature which is room temperature, T minus T0 is 0, and we have rho, which is rho 0. So what's happening is that this resistivity of the material, which this wire also is a resistance. I'm just putting this wire because it's also resistance. Okay, although very small, it just has some resistance, as I have shown you. The wire has a resistance. Okay, and we will see that this resistance of the wire not only depends on the cross-section area, but also the length. So as a function of temperature, the density starts from rho 0 and increases linearly, and the slope is given by this expression. This is the slope, right? But we've got really, this alpha is just another constant, okay? So when the temperature increases, the resistance increases. So you have to be really careful. Why? Because this is the simplest circuit element that we have, okay? If even this changes with temperature, then everything will change, okay, in the circuits. Especially when we have like supercomputers or very expensive devices to make some measurements or something. So in order to eliminate this bad property, okay, for the increasing resistance, they put the memories of these supercomputers in a very cold medium, and they usually use liquid nitrogen, and they keep all the all the circuits for these supercomputers in a very small temperature room, which is made cold using liquid nitrogen, very small temperatures, like minus 100 degrees or something. Anyway, so this is what we know, but also there are some other materials. So this is regular material, but there are some materials which we have this kind of dependence on the temperature. So resistivity again is the same, is like the same, like that. So it goes like that. As the temperature is reduced to very small values, the resistivity suddenly drops almost to zero, almost, not zero, but almost zero. So here, this is called critical temperature. And these materials are called superconductors. Now, the physicists' conductivity at high and high Tc, which is near the room temperature. Because if we can achieve that, if we can move this here like that, suppose this is the room temperature, then we solve the problem, because all the wires that we are using in the circuits will have no resistance, and no heating will occur, and everything will be best, and also the energy consumption will be as minimum as possible. So the people are trying to put together a few materials, combining them, and lots of investigation is done to create superconductor at a near temperature close to room temperature. It's called high Tc superconductor. It's called, the investigation is high Tc superconductors. So this is a big investigation. So people are trying to move this graph to the right as much as possible, right? Anyway, so also when you keep the material, this kind of superconductors in a very small temperatures, then really the resistivity is almost zero. So it means that everything moves like with a speed of light or something in the circuits, and everything gets so fast, and no energy consumption. With little energy, you can do lots of things, and so on. So people are really trying to put a few materials together, and doing research about this. So what about the relationship between electric field and the current density we have? So the electric field is given as the resistivity times J. This is actually Ohm's law. We will show that it's just Ohm's law. But for Ohm's law, you remember V equals IR. So we go from this expression to V equals IR. How do we do this? First of all, the electric field is given by the resistivity times the current density, but the current density is given by the current divided by the area. The current divided by the area. And the electric field is given as the potential divided by length. So suppose the length is L of this wire, the current is moving through the wire, and of course the electric field is in this direction, and we have the potential difference VB and VA. VB is greater than VA, by the way, because the current is moving this way. So potential difference, or just V is VB minus VA, divided by L is giving you the electric field. So now when we put V over L to the right hand side, V over L, now look at this expression. We have now rho times I over A, which is equal to V over L. But now we know that if you solve V from here, the potential will be equal to rho L over A times current. But now this is nothing but R, right? Because definition of the Ohm's law is that the current, whatever multiplying the current, is called resistance. So resistance is given as rho L over A. Very simple expression. This is the expression you remember from high school. Don't forget, this is resistivity. So we have to use the subscript R, okay, for rho. So now the resistivity times the length divided by the area is giving you the resistance. So resistivity of the material I listed, remember that earlier, is multiplied by the length and also the cross-section area. So cross-section area is very important. Now, which one of these cables you think has greater resistance? So this is one cable and this is another cable. So this cable is thicker, but this cable is thinner. So if we cut the same length from these two wires, okay, I have another wire which is even has greater thickness like that. Okay. Now if we cut the same slices, this will have more resistance. Okay. This will have more resistance. Why? Because the cross-section area is smaller. The lengths are the same, cross-section area is smaller. So this will be more resistive. The small one is more resistive to current. So in order to pass a high current, you need the cables as thick as possible. This is the reason that the current that we are passing through the jumping for the cars, you know, the cables are extremely big, like you know, the thickness of a finger or something, because a high amount of current is passing through these cables. The small cables will just blow or just burn as soon as you try the current to pass through them. Anyway, so we learned how the resistance is obtained from the expressions. Now, if you look at Ohm's law, okay, Ohm's law, IV characteristics. So it's very important we have IV characteristics, because although the resistance is the very simple element, there are other elements that give different kind of characteristics, like semiconductors or transistors or diodes or something. So in this IV characteristics, the current as a function of V is drawn. Okay, we are used to the notation like V equals IR. Okay, so V is like y-axis and I is like x-axis. This is the way that we think, but for us, for electronics, IV characteristics is important, and we use the current for the y-axis, and for the x-axis we use voltage, because the current is a result of voltage or the potential difference. Okay, so now for us, this is what we have. Okay, V equals IR, or I equals 1 over R times V, right? So the slope of this straight line is 1 over R, inversely related to the resistance. Now, if the resistance increases, okay, the slope reduces. So we have now this kind of curve, okay? But if we reduce resistance, okay, the current increases. So it's like that, okay? So this curve just moves along, okay, moves like that when we change the resistivity or resistance of the material. Okay, so now I would like to solve a numerical example. In this example, they say that the copper wire, just like this wire here, this is the copper wire, that's sitting there. Cross-section area, this area is not easy to measure because the radius is less than a millimeter or something. But the area is given as 8 times 2 times 10 to the minus 7 meters square. Maybe this is just a cable, just a small cable inside this very thin material, okay? I have it right there, okay? It's just the copper, very tiny copper, okay? Like that. You can barely see, so I can just make it closer to you, okay? As you see, it's like a hair, you know, very thin copper. So basically the area, cross-section area is like that. Okay, so also they say that it carries the current, which is 1.67 amperes. Okay, it cannot be like hundreds of amperes, of course, because it's a very thin wire. Find the electric field magnitude in the wire. So what is the electric field in the wire? So this is the first thing. And also, what is the potential difference between 2 points in the wire 50 meters apart? So what is delta V at 50 meters apart? Okay. So the length of the length of the wire is 50 meters, in other words. So if we know the electric field, we can directly find this potential using this kind of expression, okay? Now, the resistance of the 50 meters length of this wire. So what is the resistance? What is that? Okay, so the first thing that we would like to do is to calculate the electric field, okay? So the electric field is given as, okay, rho times J, but it's rho times the current divided by the area, okay? The resistivity from table, we can find, okay, resistivity for the copper wire, okay, is given as 1.72 times 10 to the minus 8 times the current, they give 1.67 divided by the area, which is given in meters squared. Be careful, you have to convert the area into meters square, although it may be given with different units. So the electric field is found as very small, okay, 0.035 volts per meter. Very small electric field. This is enough for this kind of current. So very small electric field. What about the potential difference? Potential difference is just electric field times the length. So delta V, of course, there should be delta V. Sometimes we call it as V, but it's delta V, right? Delta V is just the electric field times the length, which is 50 meters. So if we multiply this by 50, okay, you get the potential difference, which happens to be 1.75 volts. As you see, 1.75 volts is enough to move the electricity or the charges 50 meters away, okay? So now, what about the resistance? How do you find the resistance? It's given here, so I can just put all the values there, and when you do this, okay, the result is just 1.05 ohms. So it's about 1 ohm, very small resistance, okay? And now, this is it, right? We get everything. So we solve the problem. Now let's go to electromotive force and the circuits. Okay, electromotive force. So electromotive force, actually, as I told you in the beginning of my lecture, it's not the force, but it's just the voltage, right? Electromotive force. So it's the driving force for the charges, because usually we use power supplies, okay, to drive the circuits. So, okay, I say usually because in the space they use some other sources of power, okay, instead of regular power supply. And now let's see that this is the power supply, right? This is power supply. We say plus and minus. Of course, this is DC now. We are interested in DC power supply. So DC power supply here. And we have some kind of circuit. I don't know. Okay. Maybe it's a circuit like this. I will show you now a different kind of circuit that we have developed. So this may be a very interesting circuit, okay, which is just like that, as you see. This is a circuit, as you see, okay? So now it has a power inlet right there, okay? So whatever the circuit you have doesn't matter, but it will have some kind of inlet. So this is what we are doing. So we are not interested in what kind of circuit you have here, but what you have is that you connect the terminals of this power supply to the circuit. Okay. Now what happens is that as soon as you do this through a switch, for instance, okay, through the switch, we always put an S there to show that it's a switch. As soon as you turn it on, the current will flow, okay, and the current direction will be this way, okay, the current will flow to the right, and then of course it will go inside and do something, and then come back and then pass through again. The same amount of current is leaving, the same amount of current is coming back into the power supply. Now what's happening? It's like the water pump, right? So it just pumps all the current to this circuit, and then it helps rotating. So this is the motor that moves the current. So it produces some kind of electromotive force, which is epsilon. Okay, it's called epsilon. Now, what happens is that because this has an internal resistance, okay, it has an internal resistance. So now, if you look at this DC power supply and say that this is terminal A and this is terminal B, okay, VAB, or the potential difference will be given as the electromotive force. So this is ideal, okay, ideal source of EMF or power supply. Ideally, the potential that it produces between points A and B, let's put B there, okay, is going to be just the EMF of the power supply. For instance, these batteries have EMF of 1.5 volts, okay, this 1.5 volts, 1.5, okay. But now, what happens is that if we have now, for the ideal case, if the current is passing through here, then there is a potential difference, which is epsilon, then this must be equal to VAB, which is epsilon, should be equal to I times R, VIR, right? V equals IR, VIR. So this is the ideal source, but this is not the case actually. So as soon as you connect this circuit has some kind of resistance, okay? So it will show some kind of resistance. And we show the resistances like that. Sometimes like this. Doesn't matter. We put the value here like 1.5 ohms, something like that. Okay? So now the ideal source is that as soon as you connect the switch, whatever the voltage here is the same. Doesn't matter how much current is drawn by the circuit. Don't forget, the power supplies provide the voltage, but the current is determined by the resistance. So it doesn't really, the power supply doesn't push the current. People always think this way, right? It provides the voltage and also the current. No, the current is obtained by the circuit, and the amount of current depends on how much load you have or how much resistance you have in the circuit. So the potential is provided by the power supply or potential differences, but the how much the current is leaving the power supply, is coming back into or passing through the circuit, depends only on the equivalent resistance of the circuit. As you see, as I showed before, okay, this is a complicated circuit. Okay, this is a very complicated circuit, but the inlet is here, so it doesn't matter what kind of we have. But if you look from this side, this will have an impedance, which is called the resistance, okay? And we will just put there, okay? So this circuit will draw some kind of current, okay, due to its internal resistance. It's not going to be a very simple resistance, okay? Now, in reality, the power supplies have some resistance, but it's very small resistance, and we call this a small r instead of big R. So what happens is that the terminal voltage is going to be, okay, the electromotive force it provides minus I times R, small resistance, okay? And we can measure the resistance of the power supply by using this expression. So remember that we have this now power supply, which is just a battery, DC battery, which provides 1.5 volts, okay? So as soon as you connect this to a circuit, okay, it will not be 1.5 volts anymore. And I will show you right now, okay? But in order to show, I'm connecting two batteries together like this. It's serial connection. So serial connection, connected batteries. So one is like that, plus, so plus side is this, right? This, the tip is plus, and this is minus. if we connect another plus to minus like that, the potential just increases twice as much. So this is 1.5 volts, and this is 1.5 volts. Now here, if you look at, okay, this is point B, this is point A. So VB minus VA, or just delta V. Sometimes we call just simply V, but don't forget, V is just the potential difference. It is 3 volts now, 3 volts, because when you add them up, it's 3 volts. So it's okay if you connect the power supplies in series, but if you connect them in parallel, it's very dangerous, right? You don't do that, because as soon as their voltages are not the same, there will be some currents passing one from one of them to the other, and then it will create some kind of inner currents which will damage the battery. So battery management system for the electric cars are extremely important. Okay, so this is being done by an engineering student in our school, in our electric car group. Anyway, so now I would like to show you that when we have two, it's right there. Okay, as you see in this example, I put two batteries together like that, okay, and because it's serial connection, okay, it's just giving you 3 volts. The reason that I did this is because this LED, which is this LED is a big LED, bigger than the regular LEDs. Regular LEDs are like that, okay, with different colors, as you see, like this, okay, like that. But this is bigger because it's nice. It's seen. It gives more light, but it works with 3 volts, right? So now I put a circuit, as you see here. I put a circuit. In this circuit, I have a power supply. So let's put the power supply like that. The positive side is there, okay, the positive side, and there is a switch here. This is switch. As soon as you press the switch, okay, as soon as you press it, okay, as soon as you press it, the LED turns on like this, okay? Now, let's draw the circuit. The circuit is that the positive side is like that, and another one. So we have plus and minus 3 volts here. And then it goes through a switch, as you see, switch is there, okay? And then lamp, when it continues. So basically, these wires have also resistances, So we can also show the resistance of these wires. But what happens is this is important. So this is LED. Now, as you see, when I press the switch, it turns on. When I leave it, okay, there is nothing to flow. But when I press the button, okay, the current will flow. In what direction the current will flow? Of course, in this direction. So for this wire, the current is going this way, and then coming and passing through this thing, and then going back to the power supply again. Okay, as soon as you press. Okay, so now I would like to show a very important thing. Okay, some students are coming. Okay. All right. So I would like to show you that this 3 volts will reduce to a smaller voltage as soon as the current is passing through this, because this is like a resistance. So if this battery system has a small internal resistance, then this 3 volts will change. Okay, will drop, of course, not increase. So as you see there, the terminals A and B that I told you here, A and B, this is A and this is B. So these terminals are connected to a multimeter or just voltmeter here, right? So I turn this on to have DC voltage. DC voltage is right there. So now, as you see, the voltage that you see here, I'm just putting here, I hope that you see it. Yeah, it's 2.97 volts, right? It's slightly less than slightly less than 3 volts because it was used. So this battery was used. But if you leave some time like that, as you see, the potential just doing nothing just starts increasing back to its original value. What's happening is that in this battery, the molecules are rearranging themselves, okay, to cover up after they do a work. As you see now, the potential increased to 2.979, 2.8, okay, 98. It will increase. The potential just, so now when I heat this up, as you see, when I heat this batteries up, it even gets faster, okay, to 3 volts, okay, when I heat it up like that, okay. So batteries also have some molecules which are functions which are just okay, functioning with the room temp, with the temperature that you have. So I just put it sideways like that. I hope that it's much better. Okay, it's seen much better. Okay, it's already 2.984 volts, as you see. So the temperature is slightly increasing in the battery because it's just covering itself, or the molecules are rearranging themselves, whatever. But now, what is important is this. Okay, what is important is this. Now look how much voltage we have now. 2.98. Now when I turn this switch on, the lamp is there, and look at the voltage. The voltage is 2.26, 24, 23, and dropping and changing a little bit, right? Now when I leave it, again, it 2.8. So it will cover up again because there is a chemical reaction inside here. So as you see, 2.9 volts reduces to, okay, 2.3 volts instead of 2.93. Okay, 2. So this is the real life. This is the real life. So when you have 3 volts, when you connect to a resistance or a circuit, don't expect that this power supply will create 3 volts because it has internal resistance. But there are some other power supplies which are very expensive. Whatever load you connect, okay, their potential difference will be always the same. So of course there are some power supplies like that. So for expensive power supplies that we use sometimes in school in the experiments, so the power supplies that you are using in our labs, their internal resistance is almost 0. It means that if you just get 5 volts, if you arrange it to 5 volts, it will always stay at 5 volts, regardless of the current drawn from the circuit. Okay, so now we can show that this is just a limitation in the current, because since we have this epsilon minus IR is equal to epsilon is equal to VAB, we can solve current from here. We see that the current is epsilon divided by R plus R. So this small resistance that the power supply had, okay, is just another resistance that is added to the circuit resistance. Okay, so now we have we draw this circuit. By the way, this is the first circuit we're drawing. So this is okay, this is plus and minus. Okay, usually we use plus for the high side, so let's do this. Okay, okay, the longer side is positive, the shorter side is negative. So this is the so right, I made a mistake here, so this will be plus and minus. Okay, here plus and minus. Okay, so plus and minus, potential difference is applied V. Okay, so actually it has epsilon, which is 1.5 volts, and the terminal is A and B. Okay, and there is a switch and there is a resistance. This resistance came from this LED. It has some kind of resistance inside, right? So we have this circuit. So as soon as you turn on the switch, the current will flow always in this direction, always, leaving the positive terminal and coming back into the negative terminal. And don't forget, whatever the circuit is, doesn't matter. The same amount of the current should come back to the power supply, okay? The same amount of current is going to leave and come back to the power supply. So this is really the first circuit that we have now, okay? We have the VAB, don't forget for this case, VAB will not be equal to, VAB is equal to epsilon minus I times R if this has a little resistance like that. Usually we show the power supplies like that. The power supplies will have little resistance, but very expensive power supplies will have almost zero internal resistance, so that we have much better characteristics of the power supply, okay? All right, now let's go into some examples, numerical examples. After a few examples, I will just quit lecture. So, some numerical examples will help you understand, okay, these circuits. So, in this okay, so we have this circuit here now. We have a resistance and a battery, plus and minus. Resistance is 2 ohms. This is 2 ohms. This is internal resistance of the battery. And it is connected to a resistance. And we put an ammeter, okay, or ampere meter. This is always connected in serial, but the potential between A and B, points A and B, are measured. The potential is measured by the power supply, by the voltmeter. So voltmeter is connected in parallel. Okay, so voltmeter always connected in parallel. Why? Because it's obvious that we need 2 tips, okay, and because we have potential differences, and we have to measure the potential difference in order to measure the voltage. You need 2 points, and all you have to do is just touch, right? Touch to these points. So I have a multimeter here, which measures not only the potential differences, but also the currents. So what you do is that you just put this to voltage, okay, V measurement, and use these LEDs and just touch there, okay, just touch there. Whatever 2 points you're touching, it gives you the potential difference, like that. But in order the current, to measure the current, you have to switch this connector to this here, which shows the current measurement. Now you have to open this up and connect it there, and let the current pass through the current meter, and then go back to this point, okay, go back to this point. So the current passes through this, and then it gives you the current. It may be dangerous a little bit if you're not really careful, because there is a fuse. Usually during the experiments, if you pass more current than it can consume, it burns the fuse, so you have to change it. So you think that it's broken, but it's not actually. There is a fuse inside. So you have to be really careful when you are making the measurement, because the current is passing through the voltmeter, ampere meter. So voltmeter connected in parallel, but ampere meter, okay, connected in series. So suppose we have this thing. Now, in what direction the current will flow? Of course, from plus to minus. So the current direction will be this way. The same current will flow because there is no other branch. The current will flow and come back to the power supply again. This is the current. Now, this electromotive force is given as 12 volts. So electromotive force, or the battery voltage, or the battery that you buy from the market, is giving you 12 volts, let's say, and the internal resistance is 2 ohms. Okay, and the resistance that they connect is 4 ohms. what are the voltmeter and ammeter readings? VAB and I now. So now, how much voltage do we measure now? As you see, between A and B, I have two kinds of voltages. One voltage, 12 volts. The other voltage, which is created on the across this small resistance. If the current is passing through here, it is okay. If the current is passing through there, it must be plus and minus because the current is passing through there, right? Okay. So now the current, in this case, the potential difference will be smaller. And also similarly, if the current is passing through here, there is a VR and there is small VR there. So that VR plus V capital R, okay, should be equal to 12 volts because it's the conservation. We have 12 volts between points B and C. Say that this is point C. This is ideal electromotive force, by the way, which is 12 volts, which is epsilon, okay? But actually, it's not going to stay as 12 volts on the terminals, okay, because some current, as soon as the current flows, there is a potential drop, so that this 12 volts is the sum of these voltages here, plus and minus and plus and minus. Let me show you this separately here. So now I will put this power supply here. This is 12 volts, okay, plus and minus. Look what's happening. So this small resistance, I will put it here, small resistance and big resistance, okay? So this is plus and minus V small r, and this is plus and minus V capital R. Obviously, the sum of these two voltages, just like I added the voltages like that, if you just put a serial connection, you have to add the total voltage. It must come up to 12 volts, okay? So VR plus V capital R will be 12 volts. But this is just what? The current is this. And now VR is what? I times small resistance, but this V capital R is the same current times big resistance, okay? Big R, or capital R. So this I times R plus R, by the way, is equal to 12 volts. So the current now, the current reading will be equal to, 12 divided by the 2 plus 4, which is 6, and it gives you 2 amperes. So I will measure 2 amperes. So what about the potential difference between points A and B, or the resistance C's? Because this is our circuit, right? This is our main circuit, let's say. This small r is coming from the internal resistance. So now what happens is that this VAB, which is VR, is the potential difference is equal to just 12 volts minus small VR, right? Like that. So you have to subtract VR from 12 volts in order to find VR. So now what is it? 12 minus I times small r, which is 2. Okay, so the current was 2, 12 minus I small r, but it's 12 minus 2 times small r, which is just 2, okay? You get 8 volts, as you see. You think that it's 12 volts you are connected to 4 ohms, but actually it's 8 volts that you are connecting, okay? Because there is an internal resistance. We did this experiment. So as you see, now we solved the problem in numeric, okay, by numbers. So now, okay, so this is the end of lecture for today, and next time I will get into some other things, how the power is obtained, and also how the power is related to temperature and so on. Okay, this is the end of lecture today, guys. So please write your names to this class list or the chatting before leaving. Thank you very much.
Hocam bir kere de Türkçe üstünden bir kısaca anlatabilir misiniz rica etsem?